Alright, now that you've seen a look of what a transverse wave looks like, an example of that you're very familiar with, let's go over some more words that are associated with waves. A medium, we've already discussed, is the material that waves travel through. So anything can be the medium, as you saw from the video of the wave traveling around a baseball stadium, or soccer stadium in that case. The medium was the people. The people were what the wave was traveling through. So that is the medium. With sound, the medium is air. Unless you're underwater, then the medium would be water. With a water wave, that would be the water itself would be the medium, what the wave is traveling through. Alright? The wavelength is the length of one wave. So it's really hard to draw the wavelength of longitudinal waves, so we pretty much always do draw them as transverse waves. And as you saw from the video yesterday, the wavelength is the length from one point on one wave to the point on the next. It's this distance here. And the symbol for wavelength is the Greek letter lambda, as it shows here. On my PowerPoint, it wouldn't print the Greek letter. I don't know why, but lambda looks like an upside down Y. You need to learn the name of that. If you tell me, well, that little Y thing, I'm going to ignore you. You need to know that it's called lambda. That is its name. Alright, you don't want me to call you the little scrawny kid. You want me to call you by your name. So, it's measured in meters, always. In this class, we will always measure wavelength in meters. So if I give it to you in something other than meters, you will need to make a conversion into meters, right? But, again, this to here is also one wavelength. Okay, so, length of one wave. The frequency is the number of complete oscillations per second. So the way you would find this is, like, let's say I'm in the water, and these are water waves. If I stand right here, woohoo, this is me standing right here, and I just count how many waves pass me every second. Alright? Every wave that passes me every second. Now, if it takes 4 or 5 seconds for one wave to pass, then I'm getting a fourth of a wave per second. If it takes 4 seconds for one wave to pass, then it's a fourth of a wave every second. So it's how many waves pass me each second. That would be the frequency of the wave. It's measured in reciprocal seconds, or s to the negative 1. And for those of you who are not really good at exponents in math, that's 1 over seconds. Alright? Which is what a hertz is. 1 hertz is equal to 1 over 1 second. Alright? That's 1 second, not 15. Okay. So that is what a hertz is. So 1 hertz is 1 reciprocal second, or cycles per second. Alright? Cycles doesn't have a unit, so that's why we just have 1. So it's cycles per second. The symbol is a lowercase f. I usually write it like this instead of like that, just to distinguish it from other f's. Usually when I type it, I italicize it. That's just the way it usually looks. So just remember, it's a lowercase f. If you use a capital F, we're going to think you're talking about force, and of course that would be not correct. Alright, so let's do some more words that deal with amplitude. It's the maximum displacement of the particles from the medium from their resting point. So the amplitude, again, if I draw this wave, the resting point or equilibrium point is that dotted line, and I didn't draw that very well because it will go just as high above as it does below. The amplitude is the distance from the equilibrium point to the highest point of the wave. That is your amplitude. This is also your amplitude. What is not your amplitude is that distance from here to here. That is not the amplitude. Okay? That's the biggest mistake people make. Amplitude is from the resting point, or from the equilibrium point, the equilibrium line. That's what your amplitude is measured from. So what does amplitude show us? It shows us the amount of energy being transmitted. Since we've already discussed that waves transmit energy, if I transmit more energy, you're going to get a bigger amplitude. So if you think about it, if I have a wave and I shake it like this, alright, I have a little amplitude, meaning I'm not using a lot of energy. But if I have to shake it really, really big, alright, I'm going to get a much bigger wave, and it takes more energy for me to do that. I mean, just think about it yourself with your own hand. If you sit there and move like hand like this, it doesn't take a whole lot of energy. But if you move it a whole lot more, it's going to take a lot more energy. So the more energy that's being transferred, the bigger the amplitude. Okay. Crest is the point of greatest positive displacement on a transverse wave. So again, if I draw another transverse wave here, and it goes like this, the crest is going to be the tops of the wave. These are your crests. Alright, the crest is the top. The trough is the point of greatest negative displacement, so it's the lowest point of your wave. Some people call them peaks and valleys. So that's your crest and your trough. Alright. Now, let me get another sheet of paper here. With this one, compression, this is dealing with longitudinal waves. So if we look at this spring for a second, instead of drawing all the coils of the spring, I'm just going to draw vertical lines. Alright? And as that wave moves, those springs get bunched together and then they spread out. And then they get bunched together and then they spread out. Okay? So this would be one complete wavelength. And like I said earlier, compression waves are a little bit harder to deal with, or longitudinal waves. This is why they're called compression waves also, because they're compressed. The point of greatest pressure in a longitudinal wave. They're compressed. So this area would be the compression. It's the point of greatest compression. This would be the other compression. So the distance between those compressions would be your wavelength. Okay? A rarefaction comes from this word rarefied. Some of you may have heard the term rarefied air. Rarefied simply means very thin or spread out. So a rarefaction is the location where they're the most spread out. So this would be your rarefaction. Now, it's very important that you learn this word because when we start talking about wave behavior and we talk about refraction and rarefaction are different. They are completely different, not even closely related, and yet they sound very similar. So make sure that you get the words down in your head. Rarefaction is the point of least pressure. So a compression corresponds with a crest. A rarefaction corresponds with a trough if you're looking at a transverse wave. So your compression is where it would be the highest, the rarefaction is where it would be the lowest. Alright, and wave speed is of course how fast the wave is traveling. Wave speed depends only on the medium through which it travels. This is very, very important. Alright? No matter what I do, whether I move faster, whether I move bigger amplitude, higher frequency, it doesn't matter. It's determined by the speed that a wave travels is determined by the medium it's traveling through. Because it has to do with how quickly those particles can transmit energy from one particle to the next. If you cannot transmit the energy fast enough, then it moves really slow. So the medium is what matters. Speed only depends on the medium. Okay? Very, very important. So let's look back at the anatomy of a transverse wave. This is all the stuff on it. You have your wave length from crest to crest, right? Your crest and your trough. Now the wavelength is also from your trough to your trough. Notice this is showing you lambda is the wavelength, y is the amplitude, so this is my amplitude. Okay, that's its displacement, and the wave is traveling this direction. So this is the anatomy of a transverse wave. You'll notice the wave is traveling this direction, but the medium is moving up and down, so it's moving across the wave, which is why it's a transverse wave. And here's another picture of a longitudinal wave. As it says, compression is here. It's the area where they're the most compressed. A rarefaction is the place where they're the most spread out. Alright, your wavelength is from compression to compression. You'll notice the movement of air molecules or movement of medium molecules is back and forth, and the direction the wave travels is this direction, so it's parallel or along the length of the wave. Alright, the wave speed equation. Speed v measured in meters per second, wavelength measured in meters, frequency measured in reciprocal seconds or hertz. So speed equals lambda times frequency, because if I take my meters per second, it should be equal to meters times 1 over seconds, because that's what a hertz is. So boom, there you go. Okay, so let's look at a couple of example problems. Sound wave produced by a clock chime is heard 15 meters away, so the distance it travels is 515 meters. 1 second later, so the time it took is 1.5 seconds. What is the speed of sound of the clock's chime in air? So it's asking for speed. Okay, well, that's not the information I gave you in the equation a second ago, because v equals d over t, velocity equals distance divided by time. This still works for waves. It worked for cars, it worked for balls, it works for anything. Any velocity is a distance divided by time. So this still works. So what is the speed of sound in the clock in air? I do 515 meters divided by 1.5 seconds, and I get an answer of 343 meters per second. Okay? Alright, now the second part of this question is, if the wave has a frequency of 436 hertz, what is its period? Well, frequency is 1 over the period, so that means the period is 1 over the frequency. And if the frequency is 436 hertz, then I simply do 1 divided by 436 hertz, and I get 0.00229. So the period is 0.00229 seconds. Okay? It says, what is its wavelength? Well, I know my velocity is 343 meters per second. I know that my frequency is 436 hertz. I want to know what the wavelength is. Well, v equals lambda times f. So to solve for lambda, I divide both sides by f. So my lambda equals my velocity divided by my frequency. So 343 meters per second divided by 436 hertz gives me a wavelength of 0.787 meters. Alright, that is all for today. Now you will get a worksheet to work on and have it turned in tomorrow. Thank you. Goodbye.